Welcome to today's paper reading. Today's paper is titled, AdamW, Use Fewer Learning Rates to Gain More. This paper, titled AdamW, Use Fewer Learning Rates to Gain More, was authored by Yushun Zhang and colleagues from the Chinese University of Hong Kong, Shenzhen, China, and other esteemed institutions. It is currently under review for publication. The authors introduce AdamW, an optimizer that matches or exceeds the performance of AdamW while using 45% to 50% less memory. This reduction is achieved by minimizing the learning rate resources in Adam. The authors discovered that over 90% of these learning rates can be safely removed by carefully partitioning parameters into blocks based on Hessian structure and assigning a single effective learning rate to each block. They also found that each parameter block has a high-quality learning rate that can outperform Adam, given sufficient resources to identify it. The authors provide a cost-effective method to find these learning rates and propose AdamW. Empirical results show that AdamW performs as well as or better than AdamW on various language models, reducing communication overhead and increasing throughput by 49.6% during pre-training on specific GPU configurations. The introduction of AdamW, a new optimizer, addresses the memory inefficiency of Adam. AdamW significantly reduces the memory footprint by cutting down the number of learning rates by 90%, resulting in a 45 to 50% reduction in memory usage compared to Adam. This reduction not only eases the burden of CPU offloading and sharding but also allows for larger batch sizes per GPU. Despite these memory savings, AdamW performs on par or even better than AdamW across various language models and tasks, including pre-training, supervised fine-tuning, and reinforcement learning from human feedback. Additionally, it shows improvements in non-LLM tasks such as training diffusion models, vision models, and graph neural networks. The efficiency of AdamW is further demonstrated by its 49.6% higher throughput and 33.1% time savings during pre-training of Llama 2-7B on 2x A800-80GB GPUs. Figure 1 presents the results of pre-training the Llama 2-7B model. Panel A demonstrates that AdamW significantly reduces memory usage compared to AdamW and achieves higher throughput, measured in tokens per second, when tested on two A800-80GB GPUs. Panels B and C show that AdamW performs comparably to AdamW in terms of loss versus iteration and time, respectively, but processes the same number of tokens 33% faster. Figure 2 illustrates the process of AdamW, which assigns learning rates based on the structure of the Hessian matrix. This method uses more learning rates than stochastic gradient descent, SGD, but fewer than the original Adam optimizer. The key innovation of AdamW is its ability to significantly reduce the memory cost by simplifying the learning rate vector, V, used in Adam, thereby improving efficiency and performance in training large-scale models. The authors investigate the role of Adam's V, which provides an individual learning rate for each parameter. Recent findings suggest that transformers need different learning rates for different blocks due to the near-block diagonal structure of the Hessian. However, Adam assigns individual learning rates to each parameter, raising the question of whether this is necessary. Through experiments on generic optimization problems, the authors find that more learning rates do not necessarily bring extra gain. For transformers, they observe that similar or better performance can be achieved with fewer learning rates, indicating potential savings in computational resources. Figure 3 illustrates the near-block diagonal structure of the Hessian matrix in neural networks, a characteristic widely documented in research. The figure contrasts this structure in transformers, A, with that in various multilayer perceptrons, MLPs B, C, D, highlighting the consistent findings across different types of neural networks. Figure 4 presents an analysis of the Hessian matrix and training curves for a 3-block random quadratic problem. In Part A, the Hessian matrix of the problem is visualized, highlighting its structure. Part B shows the training curves for the problem, where the optimal single blockwise learning rate is applied based on the full Hessian. Part C focuses on the first dense Hessian subblocks from Part A, providing a detailed view of these components. Finally, Part D displays the training curves for the new problem associated with the Hessian in Part C, comparing the performance with the original problem. Figure 5 illustrates the performance of Adam with different blocks left out. Panels A, B, and C show that Adam, leave X out, achieves similar or better performance compared to standard Adam for all randomly selected left-out blocks, where X ranges from 1 to 3. Panel D highlights the performance gap between Adam and Adam, leave 1 out, across all possible blocks, indicating that Adam, leave 1 out, consistently performs at least as well as Adam and often better. Figure 6 provides insights into the Hessian structure of different parameter blocks within a 4-layer transformer model at initialization. Panels A, B, and C illustrate the Hessian of query, key, and value blocks, respectively, revealing distinct patterns. Panel D shows training curves on Tiny Llama 1B, highlighting that the default PyTorch partition leads to loss spikes in Adam Mini. However, switching to the partition strategy outlined in Algorithm 2 effectively mitigates these spikes, demonstrating improved training stability. Table 1 presents a comparison of the memory costs between AdamW and Adam Mini optimizers when applied to the Llama 2-7B model. The data is calculated based on float 32 precision. Key findings include a significant memory reduction of 47.4% for Adam Mini compared to AdamW, resulting in substantial savings of up to 50% of Adam's memory. Specifically, Adam Mini uses 28.04 GB of memory, demonstrating its efficiency in resource utilization. Table 2 presents the throughput test results for Llama 2-7B pre-training on 2x A800-80GB GPUs. The test compares the performance of Adam Mini and AdamW optimizers. Adam Mini achieves a throughput of 5,572.19, which is 49.6% higher than AdamW, which fails to run due to memory constraints. The total batch size, total_BS, for both optimizers is set to 256. In this section, we discuss the experimental setups and results. First, we trained various models including GPT-2 series on OpenWeText, Tiny Llama 1B on Common Crawl, and Llama 2-7B on Common Crawl. We compared different optimization methods such as Adam Mini and AdamW, along with memory-efficient methods like Adafactor, CAME, and SM3. We also conducted a sensitivity analysis on hyperparameters. The results show that Adam Mini performs on par with AdamW but uses less memory. Additionally, we evaluated Adam Mini on non-LLM tasks including ResNet 18, Diffusion Model, GCN, and GT, where it achieved comparable or better performance than AdamW. Figure 7 presents the training curves for A. Tiny Llama 1B and B. GPT-2-125M, demonstrating that Adam Mini performs comparably to AdamW but with reduced memory usage. The figure also highlights that other optimization methods do not perform as well on these tasks. Additionally, C shows that Adam Mini is not highly sensitive to changes in hyperparameters, indicating robustness in its application. Table 3 presents the GPT-4 evaluation scores for supervised fine-tuning, SFT, and reinforcement learning from human feedback, RLHF, on the MT bench. The scores are categorized by the optimization methods used, AdamW and Adam Mini. For SFT with LoRa, Adam Mini achieves a slightly higher score of 4.41 compared to AdamW's 4.23. In standard SFT, Adam Mini scores 5.40, surpassing AdamW's 5.37. For RLHF, Adam Mini's score of 5.68 is notably higher than AdamW's 5.54, indicating better performance with reduced memory usage. Table 4 presents a comparative analysis of Adam Mini and AdamW across various non-LLM tasks, including ResNet 18 on ImageNet, Diffusion Model on CelebA, and Graph Convolution Net, GCN, and Graph Attention Net, GT, on OGBArXiv. The results indicate that Adam Mini achieves comparable or superior performance to AdamW in terms of test accuracy and validation accuracy, while also demonstrating lower training loss for the diffusion model. Notably, Adam Mini's performance is achieved with reduced memory usage, highlighting its efficiency and effectiveness in these tasks. Figure 8 illustrates the training curves of GPT-2 pre-training, comparing AdamW with AdamW and other memory-efficient methods. The figure shows that AdamW achieves the same level of performance as AdamW but with significantly less memory usage. In contrast, other methods exhibit inferior performance on these tasks. This demonstrates the effectiveness of AdamW in maintaining high performance while optimizing memory resources. Figure 9 illustrates the training curves for SFT, LoRa, SFT, and RLHF during the alignment of Llama 2-7B. Notably, AdamW demonstrates superior performance with smaller perplexity and higher reward compared to AdamW, all while utilizing less memory. This figure highlights the efficiency and effectiveness of AdamW in optimizing the alignment process. The Adam Optimizer has been the subject of numerous studies aiming to understand its effectiveness. However, the authors point out that AdamW parameter may not be functioning as effectively as expected, sometimes leading to suboptimal results. This insight has motivated the development of AdamW, a more efficient version of Adam. The Hessian matrix, crucial for gradient methods, has been extensively studied in the context of neural networks, particularly MLPs and CNNs. Building on these studies, the authors explore the Hessian structure in transformers and propose improvements. Several methods have attempted to reduce the memory cost of Adam, such as AdaFactor and SM3, but these often come at the expense of performance. In contrast, AdamW maintains the effectiveness of Adam while significantly reducing memory usage. In this study, the authors introduced AdamW, an optimizer designed to save between 45% to 50% of the memory used by Adam. While AdamW employs a straightforward and cost-effective method for designing a learning rate for each dense Hessian subblock, it is acknowledged that this approach may not be optimal. The authors suggest that there is significant potential for enhancing the design of AdamW, and they propose this as a direction for future research. This work not only contributes to the field by proposing a memory-efficient optimizer but also lays the groundwork for further advancements in optimizing learning rate designs. Thank you for watching.